Okay, I will talk about approximations of delocalized eta invariants by their finite analogues. I'll explain what these words mean through the talk. Before that, let me just point out this is based on joint works with quite a few people on different several papers. I'm just kind of collecting some of the results from various papers. Okay. Yeah, my co-authors were listed on at the bottom of the slides here. Okay, so let's start. I will tell you what delocalized eta invariant is, but before that, let's remind ourselves the classical eta invariant of Atiyah-Patodi single. So it arises in the following context. So suppose we have a manifold, even-dimensional compact manifold with a boundary. So the eta invariant arises in the study of index theory for manifolds with a boundary. So let's denote the boundary by M. Now suppose on W, you have an elliptic differential operator, and now denote the boundary, the restriction of the operator on the boundary. Okay, and then the classical Atiyah-Patodi single index theorem says the index of dW. Well, here actually I wrote there's APS here because the manifold has boundaries, so you have to put a boundary condition in order for the index to make sense. So this APS stands for the APS boundary condition. So take this operator and then take this APS boundary condition, and the index makes sense, which is integer. Now it's equal to, there are two terms on the right. One term here, the first term here is a local term, is some differential form on the manifold W, which is determined by D. The D, I was supposed, maybe I should write dW here. I mean, so there's a W here, okay? So, and then there's a contribution from the boundary. This is the eta invariant of this operator on the boundary. And H here is the dimension, the kernel of this operator. So this is how eta invariant came about. So let me just remind ourselves, I'm sure probably everyone in this seminar knows what eta invariant is, but nevertheless, let me just go through the definition for preciseness. So here's the definition. So so the boundary is a closed manifold. So you have an elliptic operator on a closed manifold. It has discrete spectrum. So here, lambda is you go through all eigenvalues in the spectrum of the boundary of this operator. If you have the positive ones, you just put, so you define a function. So this is called an eta function. For you put complex numbers, S is a complex number. And for lambda that is greater than 0, you just put 1 over lambda to the S. And then for the negative ones, you take the absolute value, and then there's a difference. There's a minus sign here. Now, from standard analysis for these elliptic differential operators, the Wiles theorem and so on and so forth, it's immediate consequence from those sort of estimates or analysis. We see that this is a well, first this term, this function, this definition, this on the right hand side, it converges for when the real part of S is big enough. And then some standard asymptotic expansion, you can see that this is meromorphic. It can be extended to a meromorphic function on the complex plane, and actually it turns out to be regular at 0. Now, being regular at 0, this is not a trivial result, but it is true. I mean, it requires a proof. quite a few people, I cannot exactly remember who does what. Of course, Aptida Parodi-Singer and maybe Gyoki. Various people contributed to this to prove that it's actually 0. So it's regular as 0. But today, actually, I'm going to take a slightly different viewpoint. And of course, this is by so-called Melling transform. This function here on the right is exactly this term right here. Just some easy calculation, you will see this is exactly that. So the eta invariant of this operator D is defined to be the eta function, the value of the eta function as 0, because it's regular as 0. So there's that. That's the eta invariant. So in fact, let me actually mention this result, which is going to be relevant for what follows. So if it turns out, if this operator D here on the boundary, D bar, D boundary, is a Dirac type operator, Bismuth and Fried actually showed this integral makes sense on the nodes. In other words, you don't need this meromorphic extension process. You just, this integral as it stands, really here it just means you just plug in 0 for S, and this integral already makes sense by itself, okay? Now, by a change of variable, actually, from here to here, of course, it's just a trivial change of variable procedure, and you will get, so instead of writing, so I just want to write it in this form. So I will get by the change of variable from square root of t to square root of t, and then you will get this, okay? So from now on, this is the formula I'm going to use in the rest of the talk, okay? So this is the classical eta invariant. Now, what is delocalized eta invariant? So to talk about the delocalized eta invariant, which is, by the way, due to, this is a notion due to Lot. I will need to work with a covering space. So now, just forget about W, and now let's just focus on this manifold, M, R-dimensional manifold, which is closed. Now suppose I have a regular gamma covering, gamma is some discrete group, it's some regular gamma covering of M. A typical situation is M tilde is the universal cover of M. Now, you have self-adjoint elliptic differential operator on M. Now you can lift this operator to operator on M tilde. Okay, so now what is delocalized eta invariant? Before that, let me introduce this so-called delocalized trace. So take any group element in gamma. Suppose this element is not trivial. For the, by the way, of course, for the definition, and this definition here, alpha can be the trivial element. It doesn't really matter. But what's when it's called delocalized, it just means when alpha is not the trivial conjugacy class. Okay, so let this notation be the conjugacy class of alpha in gamma. So we can define a delocalized trace associated to this conjugacy class of alpha by just mapping any finite sum like this by summing up the coefficients in front of elements that actually lie in this conjugacy class. And it's easy to check this is actually a trace, and so on and so forth, okay? So that's the delocalized trace. For any conjugacy class different from the trivial conjugacy class, you can associate a delocalized trace. And now the delocalized eta invariant of this D tilde here at this conjugacy class is defined to be this. It's really just the same formula as before, but now replace the standard trace by this delocalized trace, okay? So we work over some covering space, and then we use the same formula, but this time we do this delocalized trace, okay? All right, of course, now, as I mentioned before, to really verify to define classical eta invariant, there's some verification why the integral converges and why it's, if you use a meromorphic function approach, well, you have to verify it's regular at 0, or you, in this Bismuth-Fried approach, I mean, you have to, there's some, you know, some magical cancellation work you have to do to make sense of this integral. I mean, it's integrable. It's actually absolutely convergent in this integral, but there's work to do. So, I mean, it's the same thing here. I mean, when I write down this formula, so far I have not made sense of this in this generality. So there are actually, to say this integral actually makes sense, there are some conditions to be imposed. So here's, let's actually talk a little bit about how it's, in what kind of context or under what conditions this integral actually makes sense. Before that, actually, let me point out, if you don't assume any condition, for example, there are counterexamples in the sense that there are examples by, for example, Piazza. I think I left, sorry, there's there's A here. Piazza Schick, actually, there's some examples you can show that if this d tilde you don't, if d tilde is not invertible, or if there's no spectral gap at 0, then there are examples where this integral does not converge. Okay, some quite explicit example actually. So what it's the minimum sort of in general, the minimum sort of condition to impose is, so d tilde has to have a spectral gap at 0. So now you wonder, is that enough? So before that, let me just point out, the issue is not at any given time t, this term here, the integrand, is always finite. That's not the issue here. The issue here is when t approaches 0 and when t approaches infinity, whether this function is integrable or not. Now, there is a difference of this delocalized eta invariant, the convergence of these guys, from the classical one. The classical one, what really happens is when t goes to infinity, if you look at the classical one, if you look at this term right here, when t goes to infinity, actually, because it's on a closed manifold, there's actually no issue. So the difficulty actually to prove this actually convergent in a classical setting is when t goes to 0. Okay. Now here actually the situation is kind of reversed because we're dealing with a delocalized trace. The problem actually here, this term here, when t is small, there is actually no issue. Now the issue is when t is large, because you are now summing up a lot of terms here, because you are summing up all the elements in the conjugacy class of alpha. So the issue is actually when t is large. So together with Chen Wan and Guoliang, we'll be able to prove that if the spectral gap as 0 of this d tilde as 0 is sufficiently large, I'll make sense what the precise meaning of sufficiently large is. Then this delocalized eta is always absolutely convergent. Okay, this integral is always absolutely convergent. So what is this sufficiently large mean? Hold on, am I going too fast here, or so? Because now my sense of I guess time is kind of lost after being quarantined at home for so long. Yeah. So are there any questions? Okay. Okay. So let me just, yeah, what is a sufficiently large spectral gap here means? It means the spectral gap of 0 is larger than some specific number here. The number, let me explain. There's K alpha. This K alpha is really just measuring how fast the conjugacy class grows. It's the exponent in the, the conjugacy class grows at most exponential speed. And this is the rate of the exponential speed, okay? It could be even less, it could be 0 because, if, for example, if the conjugacy grows sub-exponential, then you can choose this to be. So it's really just measuring how fast the conjugacy class grows. And then the CD here is measuring the so-called propagation speed of the operator D. Now, when D, for example, CD is 1 if D is Dirac, okay? So in a geometric situation, you can, without loss of general, you can always assume CD is just 1 by normalizing things. Now, C alpha here is basically a constant, the distortion constant between on the length, so L, oh, by the way, I forgot to mention this L here, this little L is some word length function on the group gamma. So since gamma acts on the covering space, so you can take an orbit of gamma, of any orbit of this gamma inside M tilde. So this, then of course you can, gamma inherits the distance from the orbit inside M tilde. Now the distance on the orbit and the word, or the original word length metric, there is some, it's quasi-isometric. So this is the constant, just measuring how, in this quasi-isometry. We only need the large time behavior. So it's asymptotically, this is the constant, the largest positive number to measure the difference between the word length metric on gamma and this orbit distance borrowed from the orbit on gamma. So anyway, so yes, so with, so then you have this constant right here. If the spectral gap of D is greater than this constant, then we say it's sufficiently large. Then our theorem says, in this situation, this delocalized eta here is always absolutely convergent. Now, as an immediate consequence of this theorem, let me just point out that if the conjugacy class has sub-exponential growth, then sufficiently large spectral gap, it just means there is a spectral. Because in this case, as I pointed out, in this case, because you can pick K alpha to be 0. So any spectral gap is automatically sufficiently large. And then in this case, this integral is always absolutely convergent for any operator with a spectral gap at 0. Okay? All right. So great. Now we have a formula, and we know in some situations, this delocalized eta invariant is well defined, is absolutely convergent. And of course, there are other situations where this this is absolutely convergent. For example, if you have some smooth dense subalgebra of the reduced sister algebra and so on and so forth. So there are other situations, but let me, since that's not the main focus of this talk today, so let me just move on. So now we have a formula. And we want to talk about. Well, how computable is this invariant? So, well, before that, let me point out. Delocalized eta invariant actually are very useful in a lot of studies, in geometry and topology, especially in the study of, for example, the space of positive scalar curvature on spin manifolds, and manifold rigidity problem in topology. So it has a lot of applications. It is an important invariant. So to use it, of course, we somehow has to compute it one way or another. So before we move on to talk about how we actually try to understand delocalized invariants, delocalized eta invariants in general, let me just give this example. So suppose L is a three-dimensional length space. Yes.
We have a question here from Cameron.
We have a what?
We have a question.
Oh, okay. I don't hear it.
Cameron.
Yes, Zhizhang. Hi, I have a question real quick.
Yeah.
Is there any sufficient condition or some conditions that you can, on the original manifold and the original D on M, that will guarantee this your sufficient condition on the lift?
Just the condition, you mean to satisfy this spectral gap condition, this guy here?
Yes, yes.
Just give me a manifold, and of course, you see, give me a specific, if you know everything. I mean, all these actually can be computed. Now, to really, then, okay, the spectral gap of this guy right here, for example, the spectral gap. So, well, of course, now, if you just give you a D, I mean, whether to compute its spectral gap probably is not so easy. But in a geometric situation, for example, if you have a positive scalar curvature metric on a spin manifold and an associated Dirac operator, then the spectral gap of D is at least, is bounded below by the positive scalar curvature. So in that case, you can at least, then you can compare in a situation like that.
Right. Okay, thank you.
Mm-hmm. Okay, are there any other questions? Okay, so let's move on. So now let me just compute this, at least give you one example where this eta invariant, delocalized eta invariant actually can be computed. So let's take L to be three-dimensional length space with a standard metric. Say the orbit space. So yeah, I mean, let me just be specific. Here's an example about a three-dimensional length space. Take S3 and you let the Z-ma P, the cyclic group, acts on S3, which is the generator of Z-ma P acts on S3 by this formula. Think of it, here I'm thinking of S3 as sitting inside C2. Okay, S3 sits inside complex, two-dimensional complex space. Now, to compute, so then in this case, you can ask, so the fundamental group of L is Z-ma P, and S3 is a universal cover in this case. You can ask the associated operator on L, which is the corresponding Dirac operator. You can ask its delocalized eta invariant at some element from some conjugacy class of some one element from the cyclic group here. Okay, so in this case, here's a computation. So first, you notice that you can extend the action of this cyclic group on S3 to the bounding disk D4. And of course, once you extend the action is not free anymore. There's a single fixed point of this action at the origin of the disk. Now, in this case, the equivariant Atiyah-Partotti-Singer theorem, index theorem, I mentioned Atiyah-Partotti-Singer index theorem. This is an index theorem for manifold with boundary. So here's the equivariant version. Think of this as some type of Lefschetz fixed point theorem. So apply this theorem, you will see that the eta invariant, this delocalized eta invariant of D, I should say this is d tilde, I mean. D tilde is on this cover here, right? So this delocalized eta invariant, and any element here actually is very computable. There's some local contribution from exactly that fixed point. So I'll leave out the explicit formula, but it's very explicit, and it's just, you can just compute it. It's some number, you really see it. Here, let me just point out so if you've been careful, if you probably noticed that, the APS, the Atiyah product distinct index theorem, actually says there's eta and then there's the index. The index is supposed to say the index of something, right, is equal to, in this case, it will be the index of the operator on the four-dimensional disk. The equivariant index will be some local contribution and then some local thing. Sorry, what is going on? And then there's eta, 1/8, eta over 2 or something like that. So let me just point out here, the index term, this term actually goes away. This is because of positive scalar curvature metric on D4, okay? You can extend the standard round metric of S3, which has positive scalar curvature metric. You can extend it to a positive scalar curvature metric on D4, which is the product structure near the boundary. So this is why in this calculation, this term actually goes away. What's left is, so it's just 0. And that's why you have this formula here. All right, so here's a computation. So at least in some cases, the delocalized eta invariant is computable, especially when the group involved is finite. In a geometric situation like this, it can be computed, okay? But in general, unfortunately, it's very difficult to compute this eta invariant in general, this delocalized eta invariant. And this brings us to the main sort of topic of this talk. So before this, that was just preparation. Now, so why we want to talk about, why we care about approximations of delocalized eta invariant by the finite analogues. So the point is, because this guy in general is very difficult to compute. As the previous example shows, when a group is finite, there is, especially in a geometric situation, there's hope to actually compute this delocalized eta invariance. So now, so it will be good if in some situations, if I can approximate this guy, which is some gamma covering, by some finite sheeted cover, the delocalized eta invariant on some finite sheeted covers. So this appears as a limit of this finite, this delocalized eta invariant coming from finite groups. Okay, in a finite group situation, as I said, hopefully, in a geometric situation, we do have tools to compute those. So to make it precise, here's a setup. So I have a regular gamma covering space of M. Now suppose gamma J, this is a sequence of finite index normal subgroups of gamma. And I denote M gamma J to be the associated finite sheeted covering space. It's just M tilde modulo this subgroup, right? This normal subgroup. Okay. Now, let me denote the quotient morphism from gamma to gamma mod gamma J by pi J. So now fix an element which is a non-identity element of gamma. Let's call it alpha. Then on this M tilde here, you have this D tilde, which is the lift of the operator D to M tilde. And now let me denote the lift of D to these other finite sheeted covering spaces by D gamma J. So now you have a sequence of finite sheeted covers, and you have all these corresponding lifts of D living on them. And of course, on these finite sheeted covers, you can define the delocalized eta invariant associated to, well, alpha is mapped to pi j of alpha. So I want to, so really we're considering in some sense the same sort of conjugacy class for the same element. This is the conjugacy of alpha. This is the conjugacy class of pi j of alpha. For this conjugacy class, you define the corresponding delocalized eta invariant for D gamma j. And then, so now the question is this guy here, the delocalized eta invariant on this big cover, on this gamma covering space, can it be approximated by these finite analogues? So in other words, is the limit here the same as that? Well, of course, provided, you know, all these are well-defined. It turns out in the finite, when you have a finite group, these are always well-defined, actually. There is no condition here. Even if there's no spectral gap, this is still well-defined. So in a finite situation, this is not a problem. So this question only makes sense, you know, if the left-hand side is well-defined. Now let's, in the following, let's actually just work in that situation, okay? So that's the main question of this talk. How can we approximate the delocalized eta invariant on a big cover by some finite analogues? So, and then, so in the following, I will talk about a couple of, so in our paper, we proved a list of results given, you know, sufficient conditions, in various sufficient conditions where this limit, you know, this question is, this equality holds, okay? All right, so let's, the first thing actually, there are some minimal requirements for this limit for this equality to hold. So the first thing is the so-called conjugacy separability. Now this, of course, you know, when you take the conjugacy class, this is a conjugacy class in gamma, when you push downstairs in gamma quotient, gamma mod gamma j, I mean, you might obtain more elements. In other words, it's possible, it's very possible you have an element that's not in, which is not conjugate to alpha, but when you push it in the quotient, it becomes conjugate to pi j of alpha. So in order to have any hope of what this limit actually holds, we need to make sure that when we need to have this so-called conjugacy separability condition here. In other words, this is, it just says when you have any two elements of gamma, a group is called conjugacy separable for any two elements in gamma. If they are not conjugate in gamma, then there exists some finite index normal subgroup of gamma, such that in a quotient here, gamma 1 is also not conjugate to gamma 2 in a quotient. Okay, so this, which means as for any two elements here, in some finite quotient, the conjugacy being conjugate is preserved, upstairs or downstairs. So, okay. Well, since for our delocalized, so this is a condition on the entire group. Since for when we define the delocalized eta invariant, we only care about one conjugacy class at the time. So we can make, this is sort of a specialization of the above definition. We only need to care about this conjugacy class, then we can make a definition. We say alpha is conjugacy distinguished by a sequence of normal index, finite index normal subgroup, gamma j, if any element in gamma which is not in a conjugacy class of alpha, then there exists some k here, which means, you know, for sufficiently large j, this quotient, and beta is not also not in, sorry, this is supposed to be pi j alpha, okay. This is the conjugate class of pi j alpha. In the quotient, beta is also not is not conjugate to alpha either. So, okay. So with this conjugacy separability, then we'll be able to prove before that. Okay. So before I state the theorem, let me just point out again, as I said, the issue really happens when you take this integral in this. So for each fixed time t here, for each fixed time t, actually, there is no issue at all. I mean, this is the integrand. This is the integrand that appears in the delocalized eta invariant. This lemma says if alpha is a non-identity element, non-trivial element. Now, suppose its conjugate is distinguished by a sequence of finite index normal subgroups, gamma j. Then this, for each fixed time t, this trace, this integrand here, right? This trace, when j goes to infinity, then it does converge. So pointwise, in other words, if you look at this integrand as a function, then pointwise, it does converge to this delocalized this function on this big cover. Okay. This is really it follows from some standard finite propagation estimates. Really, in some sense, what it really boils down to is just if you look at a finite sums of group elements like this, then under the conjugacy separability condition above, then it's trivial to see that this actually converges to this if there are only finite many terms here. Now, of course, if you look at this heat kernel, d times the heat kernel like this is not finite propagation, of course, but it can be approximated very well by finite propagation ones. So then, so the lemma follows. Okay, so this is not a very difficult lemma. I mean, of course, there's some work to do, but it's not very difficult. All right, so when t is fixed, we see that there's no issue of this convergence of this limit. All right, so the issue is, of course, what we really want is, let me do this. You know, we want to, whether, you know, to have some integral like this, the integral is inside, okay? So the point is you cannot present, the limit of the integral does not commute in general. So here's one of the theorem we prove is the following. So this is goes back to this large spectral gap that I mentioned before. So if you have an alpha group element, which is not an identity, its conjugate is distinguished by a sequence of finite index normal subgroups. And suppose the spectral gap of the d tilde is sufficiently large. Then this delocalized, this finite analog of, you know, this delocalized eta invariant, it does converge to the delocalized eta invariant on the big cover, gamma cover. Okay. So let me just point out, though, as I mentioned, you know, sufficiently large spectral gap. Here, actually, the condition being the spectral gap of d tilde being sufficiently large is slightly different from the condition that we used before, in the sense that the constant being sufficiently large, then what constant? That constant is slightly different, but it's also a very explicit constant, okay? Okay. Well, in any case, yeah, so we have a theorem like this. So of course, to prove the theorem, there's a list of estimates we need to do. But ultimately, it really boils down to this, because we've seen that in the previous lemma, these terms, point-wise, this converges to that. So now, what we, the sketch of, the idea of the proof is we actually, with this spectral gap of D being sufficiently large, guarantees us to find a function that to dominate both these two, all these functions. So then you can just apply the dominated convergence theorem, okay? So the spectral gap being sufficiently large guarantees a dominating function, okay, of these functions for all j and for this function as well, all together. All right. So that's one of the theorems we proved. So by assuming large spectral gap. So notice here that when we assume the spectral gap being sufficiently large, then there is no condition on gamma at all. So gamma can be any group as long as this conjugacy class satisfies this condition right here. All right. So now there is also other type of theorems, convergence theorem we can prove without assuming sufficiently large spectral gap. But then we have to appeal to something else. So here's another theorem in the relation to the Baum-Connes conjecture. So let me explain the statement. So this is another theorem we proved in the paper. Suppose so the conjugacy distinguished condition, that's the same. You have some element which is conjugacy distinguished by a sequence of finite index normal subgroups gamma j. Now suppose d tilde, this operator on the gamma cover, has a spectral gap. Okay, just has a spectral gap at 0, not necessarily large. You know, for example, when d tilde is invertible, just that's enough. Now, on the other hand, suppose gamma satisfies the maximal Baum-Connes conjecture. The rational version is enough. Then this limit always exists. Okay. Now, as you probably notice, this theorem is not really it's slightly different than this statement here. This statement says this limit exists and it converges to this number right here. Here, I only say, you know, this limit exists. I didn't quite say that this limit is the same as this. The only reason is because just with the condition above, it's not clear whether, it's not clear whether this term here is well defined without the assumption of spectral gap being sufficiently large. So in this generality, we don't know. But there are situations, let me actually write it down. So here, this question didn't really talk about the convergence to this guy or not, right? But if with, if the group is more special, then indeed you can actually show in this context without the, I'm not saying so it's still the spectral gap might not be sufficiently large, so it might not be large, but still if there are situations where this makes sense, and then this limit is actually equal to that in some geometrics, or if you put extra conditions on the group, okay? But let me, for this theorem, for now, let me just leave out this term for the moment. So let me just explain that this limit here actually exists. In fact, this limit has to stabilize at a finite step, which means when j is sufficiently large, this sequence of numbers becomes constant. So before I move on, let me actually talk about a little bit. I think I still have a bit time. So in the following slides, I will talk about sort of a main idea how to prove something like this and why is it related to Baum-Connes. And So here I use the maximal version, and then if the time permits, I also comment on what happens if you replace the condition of maximal bound cone by reduced bound cone. And if there's still more time, then I'll comment on the situation. You can actually talk about the limit of this is equal to that. Okay. In this sort of context of bound cone conjecture. Okay. All right. So before I move on, let me just point out there is a quite large class of groups that satisfy the maximal bound cone conjecture. This is due to the work of Hickson and Kasparov. They show that if gamma is an AT-mutable group, that means the group acts on a Hilbert space properly and isometrically. Then gamma satisfies the maximal bound cone. Well, of course, in this case, they also show that satisfy the reduced bound cone. In fact, they show gamma, Hickson and Kasparov, they show gamma is so-called K-amenable. So, but anyway, so just want to point out, so there's some content to this theorem. So indeed, for AT-amenable groups, this limit always exists. Okay. So here's sort of the sketch of proof. The idea is not, once you put all the gadgets in the right place, actually the proof is not quite, it's relatively straightforward. So first, for simplicity, let me just assume d tilde is invertible. Of course, the exact same proof would work if you assume d tilde has a spectral gap at 0. Now, in this case, if d is invertible here, d tilde is invertible, then you can use invertibility to define a maximal higher row invariant in the K-theory of some sister algebra. Oh, here is supposed this. And there's some sister algebra. So for people who are familiar with this, I apologize, I probably don't have time to explain what this algebra is. This is where the K-theory of this algebra, this K-theory is where these are secondary invariants, where these secondary invariants live. Okay, so essentially it's safe to think of this. Although I'm not going to define what the explicit definition of what is a higher row invariant. Give this the precise definition of this higher row invariant, but its relation to the delocalized eta invariant is this is the K-theoretic counterpart of this delocalized eta invariant. In fact, in the sketch of the proof, in the next slide, you will see that the delocalized eta invariant is the evaluation of these guys. Okay. So you can use the trace to evaluate on these guys to get the delocalized eta invariants. So this is, okay, but anyway, let's move on. So for these finite covers here, you can also define the corresponding higher row invariant as well. Then now the covering space, I'm talking about the covering space from M tilde to M gamma J. So it's, think of this is of course the intermediate cover between it's the intermediate cover between M tilde and M. So of course M tilde is also a cover of this guy. This covering map induces a naturally induces a folding map from this algebra to this other algebra, okay, which actually maps. So for people who are familiar with this, higher index theory, I'm sure you've seen this folding map in the context of index theory. So, but in this secondary invariance, it's still true that it maps the maximal higher row on the big cover here to the cover downstairs, or the row invariant, higher row invariant for the cover downstairs. So this is the details can be found in our recent paper with Hao Guo and Guo Liangyu. So it just means the maximal higher row invariance for these invertible elliptic operators actually are functorial. This is the counterpart for secondary invariance of the classical functoriality for maximal index, the maximal higher index. Right? Okay. So now, with this functoriality of higher row invariance, then we're in business. First, notice that for inch j, the delocalized eta invariant, the way we really care about, is actually 1/2 of that is really the same as some evaluation over this maximal row invariant. Here, this is some determinant map. So this is some determinant map induced by the trace map. Okay. So this is induced some from this trace map here, some determinant map. Okay. So first you have this. Now suppose the maximal, so here's where the maximal Baum-Connes conjecture enters. So if the maximal Baum-Connes conjecture holds for gamma, then the maximal row algebra on the gamma covering space, this is on M tilde, is the boundary, the K-theory boundary of some finite propagation element in a reduced system algebra. Oh, sorry, that's not reduced. I'm supposed to say max, okay. That's the maximal, the K-theory of the max. So this exact sequence here is this long as a 6-term long as a sequence of K-theory system algebras, and this is the the usual connecting map, mapping from the index K-theory of reduced maximal system algebra to this the K-theory of this algebra here. All right. So we're almost there. We're almost there. So here's the end of the sketch of the proof. Now, it turns out this boundary map here. So we mentioned about this boundary map. Let me maybe write it down again. So here I said the maximal row is the boundary of some maximal projection or idempotent. So then actually the determinant here is compatible with the trace map on here. So in other words, the trace on this guy, sorry, let me actually first push everything to this finite cover setting. And then there, everything will make sense actually. So the determinant here makes sense, the trace here makes sense. Actually, the determinant of the row invariant is the same as the trace of this idempotent. And then to summarize, we just show that the eta invariant, delocalized eta invariant, is the same as the trace of this Pj. But Pj is only, it's the image of P max, but there's only finite many terms in here. And then under the conjugacy separability condition, it's trivial to see that these guys stabilize in the end. Okay, and that's the end of the proof. So that's the last slide on my talk. Okay. Let me just stop here, and then maybe people have some questions. Thank you.
Thank you.
Sean has some sound effects here.
Very good.
So any questions or comments, please? So Cameron, please, again.
Yes, I have a quick question. So what are some good examples or non-examples of this condition, you know? What
are the good examples for what condition?
For the condition on gamma, fundamental group. And how do they translate to the manifold itself? Some examples or some non-examples.
You mean for the convergence, or for which question? You mean for this question, or
you
for
put
this?
some condition on gamma, right?
Yes.
Separability conjugates to separability, I think you called it.
Oh,
right?
you mean the conjugacy separability? What groups satisfy that? You mean?
Yes, and what manifolds will have that sort of fundamental group?
I mean, the issue here, I guess, is not really what kind of manifolds have that. I mean, because in higher dimensions, any group can be realized as a fundamental group of some manifold. So I guess you're saying, okay, maybe let me answer the first question. For what kind of groups satisfy conjugacy? It's conjugacy separable. Well, the examples are, for example, the free group of two generators, n generators, SL2Z, SL2Z, or groups like that. But okay. But unfortunately, for example, maybe a more exciting example would be, for example, SL3Z. Does it satisfy separable conjugacy separable condition? The answer is no. So for actually SL and Z, when n is greater than or equal to 3, they are all not conjugacy separable. Yeah, I mean, there are some, for example, okay, so of course, maybe I think I forgot to say this. Of course, a natural context for this sort of question is when gamma is relatively finite, right? Because you want to have enough finite index normal subgroups. That's probably a natural setting where you want to work with.
Right.
But for many relatively finite groups, they actually don't satisfy conjugacy separable condition on the nodes. But of course, on the other hand, if you take a relatively finite group and you look at its profinite completion or something, then any profinite group like that would automatically satisfy conjugacy separable condition. But maybe from Baum-Connes conjecture point of view, those groups might not be that exciting,
Thank you.
Mm-hmm.
I've got a quick question.
Yeah.
So on page 15, this 15.
Yeah.
Yeah. So, is there hope that this equality between the limit and the thing in the circle is always true? Are there any examples where, say, the right-hand side is not well defined, but the left-hand side is?
Well, in general, as I said, it's not known in this generality as stated in the theorem here. It's not known whether this is finite. Okay. Mm-hmm. Now, let me just talk about if there is. So here's a more specific situation. Suppose if, in addition, you assume that gamma so I'm talking about maximal Baum-Connes here, but let me also talk about the reduced system algebra of gamma. So suppose that algebra has, the reduced system algebra of gamma has a subalgebra which is smooth and dense. So which, in other words, it's a dense subalgebra that is closed on homomorphic functional calculus. And suppose, in addition, this trace here extends. So this trace a priori only defines on this group algebra, on finite sums of elements. But suppose this extends to this algebra A. Then, in this case, this term is always well defined. Right. And in this context, then actually these two are the same. Okay. Mm-hmm. If you have these extra conditions.
Right. Okay.
Yeah.
Any more questions or comments? So Zhizhang, can I ask a question?
Yeah.
So in your results, you have assumed, operator, the Dirac operator to have spectral gap. And also you pointed out that there are counterexamples that when D does not have a spectral gap, then
Yeah.
the invariant is not well defined. So my question is, do we know any examples that D does not have spectral gap, but the eta is still well defined?
That's possible. Yeah, that's possible. But for example, as I mentioned, in the, sorry, I think probably it's very dark here because it's we're having a thunderstorm. So
there is a hail going on.
oh, I see. Okay.
I mean, your eta invariant brought all those trouble.
It's disastrous.
Are you sure it is regular at 0?
Yeah, well, I don't know. Maybe they're angry at us. It is regular at 0. Unfortunately, no matter how angry they are, it's regular at 0. Yes. No, so let me see. Without the spectral gap condition, if the group is, for example, finite, then, as I said, any operator, there's no spectral gap assumption at all, and you can do it. So in a finite, in other words, for these elements here, we're not really using any spectral gap, okay?
Yes.
But for in this theorem here, we do use the spectral gap at some point, and as you probably noticed, because to define this higher row invariance, we do need the spectral gap.
Right.
But for your question, yes, I mean, in principle, it's possible, but I don't know any examples.
Okay.
Yeah, under the spectral gap condition, whether the delocalized eta exists or not, in general, it's also still an open question.
Yeah, it's still an open question. So what we showed is when the spectral gap is sufficiently large, then it's always convergent. But yeah, but I think, yeah, that's actually an interesting question, because interesting, it's probably not so easy, but on the other hand, it's interesting in the following sense: to really, to get rid of the spectral gap being sufficiently large, if one can get rid of that condition, to study the convergence, without that condition, it's actually quite related to the Baum-Connes conjecture itself,
Okay, thank you.
Yeah.
Thank you. So do we have any more questions or comments? So before we stop for today, let me remind everyone. So starting from next Wednesday, we will move our seminar 1 hour early. So we will start 1 hour early. I will remind everyone in my email next week too. So please mark your calendar so that it will not be confused. Okay, so let's thank Zhizhang again for beautiful talk.